through the lens of our use case involving a cloud-based flight simulator. So I'll begin with the question of why we would want to do this. Why would we move to the uncertainty of the cloud from the safe, reliable confines of on-premise equipment? I'll discuss the difficult challenge this move brings with us in terms of latency and bandwidth and the techniques we've adopted to mitigate these problems. I'll talk about the challenge of dynamically adaptive software, not software that is built with the sophisticated ability to dynamically adapt. Sorry, excuse me one second. Not software that can just dynamically adapt off the shelf to its environment, but this could be open source, commercial, third party, or maybe even software written in-house that you just can't afford to touch. And I'll finish with a brief look back at the fundamental architectural paradigm that drove our design. Okay, so somebody's taking now to try and ring me. Okay, so the goal of a charity is to deliver a framework for XR application providers such as Collins, and we're just one of a number of partners occupying this role. So we're going to hear from VitCheck soon about the collaborative gaming, and we've also got use cases. Pretty impressive use cases in VR medical training, tour creation, and real-time holographic experiences. So very early on in the project, we recognized that our ambition and the overall ambition of charity itself couldn't really be satisfied without a significant reimagining and redesign of a flight simulation pipeline. It couldn't be just a matter of taking an existing application that had been very purposefully designed to operate in a local closed loop environment with everything running from everything running within arm's reach on dedicated and segregated hardware, and then chiseling it apart and running pieces spread across great physical distances. So in many respects, we started from scratch. And we adopted this containerized microservices architecture using cloud native principles, which we could use to leverage the charity framework. So moving to the cloud. So where we are today, and in common with many kind of training simulators, it's when you need low latency, high bandwidth applications, such as a training simulator, then the traditional approach has been to dimension and deploy all the necessary hardware to the site. So this gives you control and like tightly controlling the environment. So you get the segregation guarantees, the dependability, the availability that you need. This is all under your control. And this has been the traditional approach for good reason, because it works and it's a proven winner. But it has problems. Upgrades can be painful because you have to upgrade every site, and if you've got a lot of sites, then that, and it's not just a lot of sites, but a lot of data involved in an upgrade. It can be very challenging to upgrade, and also there's the issue of hardware going out of date, having to be replaced. Maintenance can be challenging, and upfront costs tend to be quite high because you have to have all this dedicated hardware that has to be purchased and shipped on site, and they're ready for use even when nobody's using it. It has to be sitting there. So moving to a cloud deployment architecture is attractive because it tackles those very pain points of on-premise. Upgrades and maintenance is simplified a lot, and costs are only incurred in proportion to how much it's used. But while it tackles the pain points of on-premise, it creates new pain points. We no longer have this tightly controlled local environment where we have to we now have to concern ourselves with things we didn't have to worry about before. So we've got these big physical distances we need to contend with. We've got contested networks, and we have to think about prioritization. What happens when the resources aren't available? We're not living in a world of guarantees anymore. Okay. So to bring this into focus for our use case, we can see that a traditional dedicated hardware local deployment simulator using 2D screens for the aircraft windows, that requires a turnaround time, this motion to photon turnaround time of somewhere between 70 and 100 milliseconds, depending on the type of aircraft. Moving to cloud isn't going to reduce that, unfortunately. It doesn't make that budget smaller. So we have to do more work across bigger distances, and there's extra encoding and decoding steps we have to do, and if we push this further and look at XR headsets instead of 2D screens, the budget was reduced to a fraction of what it was. So now we've got a lot more work. We've got a lot bigger distances. We've got unstable environments, and we have to do it all faster than we do it today with everything on premise. So back in 2018, Collins published some results of investigations that had carried out into the feasibility of using cloud resources for the rendering of these out the window views in a flight simulator, and the findings highlighted some of the principal challenges involved in trying to pull this off. Essentially, the length and lack of consistency of links. It causes big headaches in terms of latency and jitter. So latency, unsurprisingly, is the gorilla in the room, really. If you want to distribute, then you have to have a plan for dealing with increased latency. So if we could just have everything locally as we have today, then hands down, we're going to get the best experience. But this is an expensive route. You need everything multiplied by the number of possible simultaneous users. Relocating to the edge, that can reduce the cost of the local setup because we need less equipment locally. Latencies are good, but the problem is that the nearby edge resources are limited. They don't have the kind of scalability that the cloud has, and as a consequence, so they're typically more expensive than the cloud, but the cloud has got longer, perhaps insurmountable latencies, depending on what it is you're trying to do. So the cloud is the cheapest, but the local is probably the most reliable. So a big consideration with a flight simulator is where we provision our terrain database. This is pretty big, and it's not something that you can just move around quickly with a few keyboard taps. This can grow into hundreds of terabytes. If we distribute it locally, as we do now, then it not only drives up the cost of local infrastructure, but it makes updates a headache, as we've got so many remote copies of the data that we have to refresh if we want to update. We could put it at the edge, but if the devices are geographically dispersed, then we have to use edge infrastructure in different regions, and we have to distribute all our software and databases across edge infrastructure where it may be needed, and it can't really just take up residency there if it's particularly for the third-party edge. Or else we're going to get a hefty bill each month, and we still have the update difficulty. It's more manageable than previous. Don't have as many copies, but it's still cumbersome at best. So, by far the cheapest place to store the data would be on the cloud. Single centralized location. But once we move data to the cloud, then really we need to move the processing of the data to the cloud, because we can't leave the processing behind and constantly try and shift all the data back and forth. So centralizing the data means also bring in the rendering that references that data with it. So here then we have user actions triggering rendering, pulling the data, and then shipping the media stream back. So the charity, like it says, charity is set out to facilitate this scenario in many respects by hopping between cloud points of presence, prioritizing traffic, creating dedicated network slices, AI-driven orchestration, and so on. But even if it achieved the very best case scenario, the laws of physics are against supporting this. If we're trying to reliably send a user action to the cloud and in response get 4K 60 frames per second video coming back to a headset in under 20 milliseconds, then that's not really plausible. Something has to give, so we had to reconsider this. We had to reconsider the plan. So here we look at how we're tackling the latency issue, and when we talk about update latency with respect to XR headsets, then it's important to consider that there's actually two different types of latency involved. The first is rotational latency. That refers to how fast you need to update the display when the user rotates their head. And this is the familiar 20 millisecond budget that you have to stay within if you want to avoid making the user nauseous. Translation latency, on the other hand, refers to how fast you need to update the screen when the user interacts with some controller to update their surroundings. And this latency can be bigger than 20 milliseconds. And in fact, it can be significantly bigger than 20 milliseconds, depending on the type of application you were building. And in our case, a flight simulator in this kind of exploratory space has quite a generous budget. So if we have this kind of tolerance available, then how can we use it? So we had this idea of a mixed reality cockpit where we use a real physical cockpit, but with virtual windows. And as we don't need to now worry about the rotational latency of updates in the cockpit because the user is seeing the real physical cockpit, we just have to deal with the translational latency of the windows, of the rendering that's done to produce that scenery that the pilot will see outside the window. So this then started bringing us down the road. Well, if we can keep the rotational latency handled locally on the device, and then the translational latency, which has this more generous budget, that's the space that we can target with the cloud. So you could consider the headset really as being placed on the aircraft itself. With the windows being the eyes. An aircraft can't turn its head quickly. In fact, it's quite lumbersome in its movements, and this is something that we can exploit further. So, given an aircraft trajectory, we can predict with reasonable accuracy where the aircraft will be seconds ahead. In fact, depending on the flight stage, you could conceivably predict minutes ahead. So we can create this room to work, this time buffer, or as some have termed it, a negative latency, which allows us to use work carried out in the past to satisfy the needs of the present. Okay, so frame rate. For getting a sufficient frame rate coming into your display adapter is important. If you don't have enough frames, then the display it has to display something according to its refresh rate. So if I guess the dumbest thing it could do would just be would display a blank screen, and then you're going to see a lot of flickering, but more often than not, it'll just repeat the last frame it got, and then you kind of get juddering. So if your frame rate is falling behind, you'll get a poorer experience. And TVs, all the modern TVs are built to take this in their stride by doing frame interpolation. So they would, if they're not getting the frame rate they need, they will try and make up frames on the fly. And the sophistication of frame interpolation is increasing all the time. And it's growing in accuracy and in also, like, I mean, it's software and hardware. And it's becoming increasingly viable to do this in real time. And in fact, with XR headsets, it already is and has been for some time. The challenge with XR headsets, seeking to cater for fast head movement, is that by the time a frame is rendered, it may already be out of date. And even the most capable computers can stutter and lag. These headsets they'll typically warp the image slightly if there's a difference, if the head has moved that little bit since when the frame arrived. And so depending on the insight that these headsets have into the rendering pipeline, they can do increasingly sophisticated things. But I guess the takeaway really is that you don't necessarily have to render a high frame rate remotely in your rendering engine. You can generate a lower frame rate and interpolate a lot nearer to the user. And as well as frame rate, when we look at resolution, it's a similar issue. Modern TVs, they still show old movies, they still show old shows that weren't filmed in 4K or 2K or whatever. But they need to be able to display this media in the full splendor of the large screen, and it'd be pretty unsatisfactory if all these large TVs could display as a small rectangle in the middle for shows that weren't generated in the higher resolution. And games consoles do similar. They want to make sure that they work consistently on TVs large and small. And in the past, I think in the past like 12, 18 months in particular, where we've seen this rise in open source upscaling frameworks in real time level that are using modern GPUs to form quite impressive upscaling in real time. And so then so not only do we not necessarily need a high frame rate on the cloud, we don't necessarily need high resolution on the cloud, because we have the option of upscaling locally. So if we combine all this, then we see how we can reduce latency through we can predict the movement of the aircraft, and we can upscale at the edge or device, and we can build this pipeline in which we detach the cloud work from the real-time flow by pulling from this kind of a pre-filled cache of frames. Okay, so to switch gears a little, adapting to our environment. So I wanted to get back to one of the challenges I alluded to earlier when I said that moving away from dedicated local resources to this shared resource pool model that we have with the cloud at the edge. We have to make decisions about prioritization. There's even when the cloud can physically scale far beyond our needs, monetary budgets will often act as brakes. There's no scale forever. Sooner or later, either because we've exhausted our budget, or there are physical resource failures, or whatever operating constraints we have, we need to deal with scaling things back, or with limiting them. And we've been considering this model in which we don't want to break service if at all possible. It's better to avoid it's better to offer a reduced quality of service experience than no experience. So imagine if you had a site engineer at your disposal, and that, given a description of the environment that the software is running in and what its limits are, then that engineer will consider what to do, and then they'd reconfigure the application and say, right, well, you could run under this configuration. Maybe we'll turn off these features, we'll reduce that fidelity there, and we can deliver a usable experience of less quality. But what we want to do in charity is just this, but without the human in the loop, which is obviously impractical. So dynamic software product lines it's a field of software engineering devoted to the design of self-adapting systems. And generally you'll see this MAPE-K loop and applications which have been designed from the ground up to have inbuilt environmental sensors and crucially the ability to dynamically change the behavior on instruction from an outside executor. So we want to consider being able to deliver this ability to applications that were not built from the ground up with the ability to change their behavior, because really that's probably 99% of the software out there. So we consider this modified version of the MAPE-K loop, and in which we layer this service mesh over applications to allow dynamic rerouting of traffic between differently configured versions of the same containerized services. So there are key building blocks to pull this off. First, we need monitoring to observe the environment and enable application providers to configure alerting conditions, such as a resource threshold being reached or an excessive latency observed on the edge cloud link or whatever. We need a knowledge base, given a particular set of circumstances, a blueprint assembled by the application provider, probably developer, that describes the configuration options that will be provided to launch an application instance more suited to dealing with the observed environment state. So an appropriate blueprint is that it's selected by the planner, and the executor then, that's kind of where the rubber hits the road, really. That requests the orchestrator to launch an application variant. So this could be something as simple as a single microservice variation, or it could be more significant. It could be a significant group of microservices together, because sometimes there's interdependencies. You can't just restart one. You might need to do a subset. So, and it then instructs the service mesh to reroute traffic appropriately to the new variant before shutting down the original. So to summarize, the application provider, they identifies different configurations to be used under different environmental conditions. Containerization that allows us to inject different configuration options, such as environment variables, into different containers, so that we can launch differently configured versions of the same containers in parallel, and then we can switch the traffic from one version to another using a service mesh. So the concept is actually it's quite similar to what we would do if we were carrying out a live rolling upgrade of software, for example. So it gives us this continuous self-adaptive loop. Sorry, I just that can be tuned up or down, and so it targets legacy and third-party applications which they just don't have this innate ability to adapt. But their behavior can nevertheless be modified, as we'd see with the majority of software, by changing the configuration at startup time, command line parameters, static files, environment variables. Right. So just the last slide. I'd like to end on this one. So the cloud native principles, they're not just about AWS or Azure or Google or whatever hyperscaler you pick. They offer these sound principles for modular distributed software design, whether you run everything on a single box or spread across this device edge cloud continuum. So the real power of the cloud native principles is it lies in the delayability that it brings to your decision making. Will I run it here or there? How many instances do I need? What happens when I need to move software and so on. And throughout our journey, for the most part, we never really had to nail down what we would run on the cloud, what we would run on the edge, what would run locally on the device or on the machine the device is tethered to. So the cloud nativeness, it gave us this flexibility to adjust and readjust, throw things out, restart. It has costs for sure. A microservice containerized platform has more moving parts, more things to monitor, but we found the benefits far outweighed the costs. So that's it. Thank you very much.
Thank you very much. Very nice presentation. And there are questions. If no one has questions, I have one. And at a certain point during your presentation, you mentioned to put on the edge some algorithms like frame interpolation or upsampling so that you can reduce the amount of data from the cloud to the edge, but obtain high quality data for the end devices, from the edge to the end device. And but you have just tested some of these technological solution with your flight simulator or not?
That's ongoing at the moment, yes. So yes, we're getting very promising results with the super resolution and for the resolution upscaling and for the right framework for the frame interpolation.
Okay, so you have just tested successfully upsampling, and but regarding frame interpolation is something that takes into account only the video content, image content, or also the movements of the user?
No, just the image content.
Just the image content.
Yeah. We don't really concern ourselves with movements of the user. We're concerned with movements of the aircraft.
Okay, so mainly something like the optical flow of the images. Yeah, nice to know. And these techniques that you have used are some standard one or some recent based on deep learning, or
yes, we're using off-the-shelf open source. Really, that's what we're looking at. Our objective here isn't really to come up with new upscaling advances. It's our focus is on the pipeline. It's on this pluggable pipeline where we could swap in and out different interpolation technologies.
Yeah, for sure. Okay, you can exchange the algorithms if necessary. Yeah. Okay, so thank you very much. And other questions or about presentation? If not, we
Mike.
Yes, please.
This is
Anthony Salti from Orama VR.
Yes, very nice presentation. Thank you very much. If I understand correctly, the rendering of the scene is going to happen on the cloud resources. Yes. Okay, that's what I understood too. Have you really tested the quality of experience that you get on the headset?
Not yet.
Not yet. Okay. Okay, because to my understanding is it's a little far, the cloud, so I'm not sure about the latency factor.
Oh well, absolutely. But that headset is not going to be pulling frames from the cloud. It's going to be pulling frames from a cache that has been pre-populated from the cloud, and that's local. So the headset is pulling frames from the edge, and that edge. So in the case of Collins and the flight simulator, like an edge would be probably campus-wide infrastructure. So if we had a flight academy or something, there would be edge infrastructure probably on campus. The cloud does the work, but it's not in the real-time call chain where we have to display on the headset. The cloud is there and it's working ahead and it's populating this cache on the edge ahead of time. So when we're using the headset and when the plane is moving, that imagery update it's happening pretty local. We're never going to the cloud and trying to, because it just wouldn't work.
So when you say pretty local, you mean on the headset or you mean on the edge?
On the edge.
On the edge. Okay. Okay. Thank you.
No, thank you.
And a comment about this, I think that this cache may be populated because the flight plan is predefined, something like this, or not.
Well,
Or
yeah,
it accounts for many hypotheses.
It's not as probably not as clunky as a flight plan. So it just predicts like so we're looking at 3 to 4 seconds ahead.
Okay.
Now, if you were in cruising stage of a flight, you could probably very reliably predict minutes ahead where the plane is going to be, and you could start generating the scenery minutes ahead at that stage. But on takeoff, ascent, descent, landing, you've got a smaller window, but still, like a flight, an aircraft is not a human. It's not a human ahead. It can't move with the same speed and doesn't require the aircraft itself isn't going to get nauseous, like, you know. The user inside, they're still getting the very fast updates of when they move their head and see the cockpit. The scenery that is outside the window doesn't necessarily have to update at the same rate as the local physical world that the user is seeing.
I got the point. Yeah. Okay. So thank you again, and we move forward with the presentation of Zvízek, and I leave the floor to you. You can begin. I see your screen.
Okay, thank you. Sorry for not sharing the camera, but it just refused to work a few minutes before we started. So I'll just leave it off for now. Okay, so hello everyone. My name is Zbyszek Ledwoń. Today I'll be talking about using Entity Component System framework to build XR mobile multiplayer games. I work for Orbital Knight, and Orbital Knight is a mobile game developer based in Warsaw, Poland. So, yeah. Sorry, it's not this one. So Orbital Knight is one of the use case providers for a charity project. And our use case goal in this project is to create a cloud-ready XR mobile application by pushing all that we can to the cloud services. It's not an easy task, so we do our best. And our use case application is a sandbox application that uses LiDAR technology to scan the environment, build mesh collider, and allow for interaction in a mixed reality. We will also attempt to merge mesh colliders from several devices using mesh merger service that will be provided by Charity. So today I will kind of list the main challenges that we face when making multiplayer mobile games. And then I briefly introduce the Entity Component System and tell you what it is, in fact. And I'll talk about the benefits of using entity component system and why we use it to develop mobile games and multiplayer games. So the obvious challenge is, of course, minimizing network latency. Mobile players are very demanding. That's why it is important aspect of the game state synchronization. And of course, we never cannot assume that we will manage to eliminate the network lag entirely. That is why our game simulation needs to be fully deterministic. It's not easy to achieve that, but it is important to allow for local prediction of the game simulation. Because if the simulation is deterministic and prediction works well on the end device, on the player's device, players are not even able to notice any network lags. And also the challenge, the very important challenge here is code organization and scalability. This aspect of the development becomes very important at the later stages of the development, when we work on game optimization and on adding new features to the game. In short, the better code we have, the easier it is to develop it and to maintain it. So the best practice is to use proven patterns to deal with these challenges, and entity component system is exactly what we need here. So what is entity component system in short? Because it's not an easy concept to grasp, but I'll try to explain it in short. So it's a proven programming pattern. It has a data-oriented design. It's composed of 3 main elements, and I will start with components because this way it's easier to understand everything. So the components are data containers. They store all the data of the game and game objects in particular, like attributes, properties, and stuff like this. For example, in a car game, this would be location of a car, direction, speed of a car, and etc. And entities are kind of groups of components, and these groups are actually the game objects that are visible and interactive in game. In a car example, in a car game example, a car would be an entity. Obstacles would be entities, and other cars also would be entities. All objects that are visible and interactive in the game would be entities. And of course, there can be multiple entities of the same type in a game, and there can be many types of entities. So you can think of components and entities in a way that the composition of components in an entity defined what kind of game object a given entity is. And then the last element is our systems, and systems are responsible for the game logic. They operate on the data provided by components and define behaviors and interactions of entities in the game. So in the car example, the car game example, there would be a separate system responsible for moving cars, rotating cars, collisions between objects, sounds the object made, etc., etc. Each system is responsible for something else. So what benefits do we gain by using entity component system over object-oriented programming? As we all know, the modern CPUs have multiple cores, and they are most efficient when we allow the cores to work in parallel. And ECS strongly supports parallel code execution because systems are designed in a way that they can work independently in the same time. Another very important, and I would say even key feature of ECS is its memory layout, which is designed to optimize cache operations and minimize page switching. And all those features of ECS allows games to work with thousands of game objects very efficiently. Also in ECS, there is no inheritance, polymorphism, and virtual functions like in object-oriented code. And this allows the code to be easier and executed faster. ECS also enforces clean separation of concerns, and this leads to better modularity of the code and better reusability of code. And this modularity aspect also means that it is much easier for programmers to collaborate on this code because they can work on different systems without causing conflicts in code. Now, for a moment, let's dive a bit deeper into memory management of entity component system, because as I said, it's a key element of the framework that allows us to run the code very efficiently. So, as you can see on the image here, entities of the same type containing the same set of components are called archetypes. And those archetypes are always kept in continuous memory chunks. Usually these are pages, and the chunks usually fits pages of memory. This is very crucial and important. So if a game is handling, for example, all cars in a game, it can do it in a single run without cleaning caches and jumping around memory pages. All the necessary data is already there in one place in the memory, and usually on one page. Because games and simulations in general usually want to work on the same type of objects in a given time. So this strategy fits perfectly to be efficient, and it increases the code execution big time. So to sum up, using entity component system means better utilization of modern multi-core CPUs and much faster code execution. ETSS is perfect for handling thousands of objects very efficiently. And this makes this framework interesting not only for game programmers, but also for anyone who would like to create any type of really, I don't know, real-time simulation. Yeah, I'd like to also mention that there are two main implementations of entity component system for Unity game engine. It's Unity Dots that is built into the Unity engine. It's very efficient. I guess it's the most efficient solution on the market so far. But it's not really easy to use. It has a, I would say, quite steep learning curve to understand what's going on in this code. But once it's done, it is worth it. It's very, very efficient. And as usually with Unity libraries, it's still in beta phase. So it's not really production ready yet. So we have to be careful about it. You can read about this at this link. And there's already a lot of documentation and information about it. The other implementation is a third party one written in C#. It's much easier to use and understand, and it's production ready, but it's not as efficient as Dots. So I guess the future of ECS in Unity is Dots. But this Entitas is good for starting with ECS games. Okay, thank you for your attention. I'm of course open to any questions.
Thank you for your nice presentation. And I have one question.
Yes.
I would like to know if you have just you are using this paradigm recently, you have moved to use it, or is something that you have used for many other applications that you have developed in Orbital Knight?
Yeah, we used it in many games so far. We started using around 5 years ago, and from this time on, we use it in every production that we made. We mainly used Entitas, but recently we developed one game with using Unity Dots, and it also is stable, but it's still in beta phase, so we needed to be very careful with it to make a lot of tests if it's.
In fact, I've asked because you've written in the slide beta test, so I imagine it is something recent. But you have just used it. You have just used the other Entitas in your applications. Okay, so
yes,
you know well this technology, this paradigm.
Yes.
Okay, and so regarding the development of how to say concurrent games like the collaborative game in Charity, you think that this model is the programming model is fruitful? Yes.
Yes,
Has
because
also other advantage with respect to the one said, or mainly is the one that you have described in here?
yes, exactly. The other benefits that I didn't say about this is the data management is much more convenient in ECS because you have all the data in one place. You can kind of deal with the data when you try to, for example, to gather all the changed information from the game state. You can easily pick the data that has changed and mark it as dirty, and then gather the information in a packet and send it through the network. And it's much easier than going through for objects scattered around the whole memory. It's all in one place and easy to manage. So it's also very beneficent for multiplayer projects.
Okay. Thank you. So now a question from Tariq Benmerar.
Hello. Thank you very much for these presentations. So the first moment I have came across this is from Acton, I think, from Insomniac Games. It has. Can you hear me well?
Yes.
Yes. It has given a presentation about data-oriented programming they have done for Insomniac, but I remembered well that he was very criticizing the C++ compared to C when going with these methodologies. So how do you think is this efficient with all the tools in C#? So did they put in place something that allow more efficiency related to this compared, for example, to the old tools you are using? Or can you elaborate about the performances?
Yes, sure.
With non-C languages in this case, and from other presentations, I've seen that you need to think a lot about how you put the information. It's not an easy exercise. You need to find a way to reduce the quantity of data that you store. It needs some thought. It's not something that you jump into and it works from the beginning. So
Yes.
I would like to have some inputs about that. Thank you.
Of course. So ECS, in fact, started when a long time ago when I don't remember the name of the company that was working on a game on PlayStation 3, and as you probably know, the PlayStation 3 has a very strange hardware architecture, and memory management there was very hard to maintain, and that's when they came up to this ECS idea, the data-oriented model of the memory management. It was on PlayStation 3. It was so efficient that everybody started using this solution there. And regarding the efficiency on the modern CPUs, the most important two key elements that are most important regarding efficiency is first that you have to have the data in as compact as possible. I mean, as close to each other as possible in an arrays or tables that are in a continuous chunk of memories. This is the most important thing, because then the cache of the processor of the CPU doesn't have to constantly clear and reload new chunks of memory. It just works from the cache, so it's very efficient. And the second thing is that you allow to run systems that are part of the ECS. You allow them to run in parallel. So they do independent work on each component, on a series of components, in fact. And this way you get the job done 3-4 times faster than with one thread. And regarding the languages that are involved, DOTS utilizes C++. I mean, Unity is under the hood is working. It's written in C++, and but it's not object-oriented code, so it's actually kind of C, you can say. And so it's very, very efficient. It doesn't get better than this, just to be honest. And Entitas is written in C#. It's very well optimized, but because the guy that wrote it is did it very well, but obviously it's not as efficient as Unity DOTS, which is working practically on a bare metal. So, but even Entitas written in C# is in comparison to object-oriented code is so much faster than that it is worth using. It's hundreds of times faster. So, but if you want to squeeze everything from any machine that you are working on, you should probably consider DOTS.
Okay. Just a little bit questions before regarding multi-cores. Do you auto limit yourself because I've seen some games where they don't use all the cores because it creates a memory bottleneck. And I have some memory about some games like that. But do you do that? So, for example, if you have 4 cores, you only use 3, or it's not an issue?
It's since we are using Unity engine, it kind of we don't have this low level of control over the cores that are we can only suggest the engine to run on that. We just write systems and tell the Unity engine to run. You can run this system separately, and what it does, if it runs it on a separate thread or not, it depends on the engine. So we don't even deal with this low level stuff.
Okay, thank you very much.
Okay, so last question from Luis Rosa. Please, Luis.
Yes, sorry. Can you hear me?
Yes.
Just a bit of follow-up of what we were discussing. I would like to know your take on how these Unity libraries and the Unity itself, when it comes to the entity component system, compares to WebXR technology and framework like A-Frame and so on.
I don't really know those technologies, so I cannot compare them.
Okay.
Yeah, but what I can say is that Unity is a very I wouldn't say it's very old, but it's quite an old engine, and it is very well optimized by now, and especially DOTS, that is obviously new, but it's still in beta because they are still working on the optimization of it, and it's fully featured now, but they just put it in still keep it in beta because they are not entirely sure that they optimize it completely. And but as I said before, we already used it for one project, and it just makes I would say huge difference in performance. But I cannot compare it to WebEx XR.
Okay. So there are no more questions, it seems, and so.
Massimiliano, I have my.
Sorry, I don't see you. Sorry, Anthony. Please, there is another question from Anthony Protopsaltis.
Okay, thank you. Thank you, Zbyszek. It was very nice presentation. One thing to say about the A-Frame is it's a web framework for building extended reality applications, and it includes the entity component system that you just presented. So it's another framework, the A-Frame, that uses the entity component system. Now about your presentation, if I understand correctly, your application is a multi-user application. So I guess that you have some kind of a cloud server that deals with this multi-user synchronization.
Yes, of course. We have two main components of our application. One is a client, of course, which runs on the device, on the smartphone, and the other one is a game server. And both those applications are utilizing ECS. Actually, is another benefit of ECS that you can write both of this application, both client and server, in the same code base. You can have them both in one place, and just run some systems on the client and other systems on the server, and it is very easy to switch between client and server in ECS.
Okay,
So
that was exactly my question, because I didn't know if in your server you keep also the entity component system that the client has. So
yes.
Okay, so you also accept the entities and the components that you also clone, you copy on the server. You also move the systems.
You're talking about the synchronization of game states, right? Did I understood correctly?
Yes, I mean, you have your clients with your ECS locally, but you also said that you have your server somewhere in cloud or edge component, edge resource, where you also have your another copy of the ECS.
Yes, exactly, yes.
Together with the service, right?
Yes. Okay. It's the same. It's exactly the same code, but on the client there are some systems that are working only on the client, and there are some systems that are working only on the server. But they are all the code base is exactly the same on both applications. So it's much easier to maintain such code also, because it's the same code, right? We don't have to write separate applications for the server and the client, but instead we write one application and just tell the code how it should behave, right? We tell it you are the server and run as a server, and you are the client and run as a client, and that's it. And the game set that we need to synchronize is all hidden in components. So the data are in components. If we synchronize only the components, then we have all the game system synchronized all over the game system.
Great. Many thanks. Thank you.
Thank you.
So, thank you again, and it seems that there are no more questions. So we can conclude this webinar, and my comment is that both the presentation are very nice and give very useful hints and information for the development of complex VXR applications. And it's all. So we can stop to record the session and conclude it. Thank you to all to participate this way.
Thank you.
Thank you very much. Thank you.
Thank you.
Thank you very much. Bye-bye.
Very well.
Bye to all. Bye.
Bye-bye.